A warm welcome to part 3 of the lecture on limits. In the previous lecture, towards the end, we introduced the concept of boundedness of a set. We also looked at the lower bound and the upper bound of a set, and also defined terms like the greatest lower bound and the least upper bound of a subset of R. In this lecture, we'll start off by making two important and rather strong propositions which will help us decide the nature of a sequence regarding its convergence without having to resort to the first principles. So let's get started. Proposition 4 states that any non-decreasing real sequence which is bounded above converges to its supremum. Non-decreasing implies that if the index n is strictly less than the index m, this implies that the corresponding term xn of the sequence will be less than or equal to the term xm. Let us see a quick proof of this proposition. Let xn be a non-decreasing real sequence which is bounded above. By virtue of the result which we had seen in the previous lecture, such a sequence will have a supremum. Let that supremum be denoted by L. So L is basically the supremum of the set formed by the terms of the sequence. Now we want to show that this sequence xn converges to L, and we will do so by resorting to the first principles. So let epsilon greater than 0 be given. There exists n naught belonging to the set of natural numbers such that this following set of inequality holds. Now let me explain to you in detail why this is true. First of all, since L is the supremum of a set, of this set formed by the terms of the sequence, we know by the definition of the supremum that any number smaller than L will fail to be an upper bound, which means L minus epsilon is not an upper bound of this set. This implies that there exists some term in this set, say xn naught, which is strictly bigger than L minus epsilon. So this first inequality is justified by virtue of the definition of the supremum. Now since the sequence is strictly increasing, or rather non-decreasing, this implies that xn naught will be less than equal to xn for all n greater than equal to n naught. And since L also is an upper bound, this implies that xn will be less than equal to L for all n, and in particular for all n greater than equal to n naught. So this set of inequalities is justified. Now it is immediate that L minus xn is less than the length of this neighborhood, which is epsilon. So L minus xn is less than epsilon for all n greater than equal to n naught. This implies that xn belongs to the epsilon neighborhood of L for all n greater than equal to n naught. But the number epsilon was arbitrarily chosen. So no matter how small epsilon is, you will always find some corresponding n naught for which the terms of the sequence xn will belong to this epsilon neighborhood of L for all n greater than equal to n naught. So by virtue of definition, xn converges to L. This is exactly what we wanted to show. Proposition 5. This is similar to proposition 4 in spirit. Let me spell it out for you. A non-increasing real sequence xn which is bounded below converges to its infimum or greatest lower bound. Non-increasing implies that if the index n is, say, strictly greater than m, then the corresponding term of the sequence xn will be less than or equal to xm. The proof of this proposition is exactly the same as the previous one, and I leave it to the reader to verify it himself. Let me illustrate the utility of the previous two propositions by means of two important examples. Let xn be the sequence xn equal to 1 minus 1 by n for all n belonging to the set of natural numbers. As we have seen already in the previous lecture, xn is an increasing sequence, and also that 1 is equal to the supremum of the set formed by the terms of the sequence, that is 1 minus 1 by n. This we have already seen in the previous lecture. Now by proposition 4, it is now immediate that this sequence 1 minus 1 by n converges to its supremum, which is 1. So xn converges to 1 as n tends to infinity. Similarly, let us consider the sequence xn is equal to 1 by n for all n belonging to the set of natural numbers. This also we have seen that xn is a decreasing sequence and its infimum is equal to 0. So again, by proposition 5, we can conclude that the sequence 1 by n converges to 0. Now you can see the utility of the last two propositions. We could conclude the convergence of the series 1 minus 1 by n and the sequence 1 by n to their respective limits, which is 1 and 0, without having to resort to the first principles, directly by using the last two propositions. So it will be our theme from now on to investigate such general results which will help us decide about the convergence of a sequence without using the first principles or definition. It is also important to mention that this particular last two propositions are critically used in showing that the sequence xn equal to 1 plus 1 by n raised to the power n converges as n tends to infinity, and the limit is the popular number e, which is the base of the natural logarithm. So far we have been discussing about convergent sequences. Let us pause for a while and discuss in some detail what is meant by a divergent sequence. A sequence xn, real or complex, which does not converge to any number L is said to be a divergent sequence. Let us consider an example. Let us consider the sequence xn equal to n for all natural numbers. This sequence xn equal to n diverges. This is because the set formed by the terms of the sequence, which is n, is an unbounded set, and hence the sequence xn equal to n cannot converge by virtue of proposition 3, which said that if a sequence converges, then the set formed by its terms must be a bounded set. Even a sequence whose terms form a bounded set need not necessarily converge. As a counterexample, consider the sequence xn equal to minus 1 to the power n. The terms of this set, of this sequence, form the set minus 1 and 1, which is clearly bounded. However, the sequence xn equal to minus 1 to the power n does not converge. We will show this by contradiction. So let us suppose that the sequence xn equal to minus 1 to the power n converges to some number, say L. Let us choose a neighborhood of L of radius 1 by 2. Epsilon is equal to 1 by 2. Since we have assumed that xn converges to L, we can conclude that there exists a natural number capital N such that mod of xn minus L is less than 1 by 2 for all n greater than equal to this capital N. This follows directly by the definition of limit. But this implies that L minus 1 by 2 is less than xn is less than L plus 1 by 2 for all n greater than equal to capital N. That means all terms of the sequence lie in this neighborhood of L, which is of radius 1 by 2. But the terms of the sequence are precisely 1 and minus 1. So both minus 1 and 1 should lie inside this interval. And therefore the distance between 1 and minus 1 can be at most equal to the length of this interval, which is 1. Now that is a contradiction because the distance between 1 and minus 1 is 2, whereas the length of this interval is 1. So that implies that 2 is less than 1, which is clearly a contradiction. Hence, our assumption that the sequence xn equal to minus 1 to the power n converges to some number L is false, and hence we can conclude that this sequence does not converge or it diverges. Now, having seen what a divergent sequence is, let us get back to the converging sequences, and let us make another proposition which says that if xn is a sequence converging to a number L, then the sequence mod xn converges to mod L. Let us see a quick proof of this proposition. Since xn converges to L as n tends to infinity, this implies by definition that given any epsilon greater than 0, there exists a natural number n naught such that mod xn minus L is less than epsilon for all n greater than equal to n naught. By the reverse triangle inequality, mod of mod xn minus mod L is less than equal to mod of xn minus L, and mod of xn minus L is less than epsilon for all n greater than equal to n naught. Hence, we can conclude that mod xn tends to mod L as n tends to infinity, or limit n tending to infinity mod xn is equal to mod L. Let me mention that the converse of this proposition is not true unless L is equal to 0. That is, if mod xn converges to a number L greater than 0, then it does not imply that xn necessarily converges to L or minus L. As a counter example, let us consider the sequence minus 1 to the power n. Now the terms of this sequence are 1 and minus 1 only. So mod xn is a sequence which is equal to 1 for all n, or in other words, it is the constant sequence, and hence it converges to the same constant, which is 1. However, the sequence xn, which is equal to minus 1 to the power n, does not converge, as we have just seen. Let us see another useful proposition, proposition 7. Let xn be a real sequence converging to a number L belonging to R. Suppose L is greater than 0, and let k be some number between 0 and L. Then there exists a natural number n naught such that xn is strictly greater than k for all n greater than equal to n naught. Similarly, if L is less than 0, strictly less than 0, and k is some number between L and 0, then there exists a natural number n naught such that xn is strictly less than k for all n greater than equal to n naught. Let us understand this proposition visually first. So xn is a real sequence which converges to some number L which is positive, strictly bigger than 0, as you can see. What the proposition says is that let k be any number between 0 and L. So this is the number k which is between 0 and L. So the proposition says that there exists a natural number n naught such that xn is strictly greater than k for all n greater than equal to n naught. That means for n large enough, all terms of the sequence will be strictly larger than this number k, and this number k can be any number between 0 and L. To see a proof of this, we can consider a neighborhood of L of radius equal to the difference L minus k. So let epsilon be equal to L minus k, and this is strictly bigger than 0 because k lies strictly between 0 and L. So L minus k is strictly bigger than 0. Now let us make use of the fact that xn converges to L. Therefore, there exists a natural number n naught such that mod xn minus L is strictly less than epsilon for all n greater than equal to n naught, where epsilon has been chosen to be equal to L minus k. So mod xn minus L is less than epsilon for all n greater than equal to n naught, where epsilon is L minus k. This means that L minus epsilon is less than xn is less than L plus epsilon for all n greater than equal to n naught. Now substituting L minus k in place of epsilon, we get k is strictly less than xn, strictly less than 2L minus k. Now, from the first half of the inequality, it is clear that for all n greater than equal to n naught, xn is strictly bigger than k, which is exactly what we wanted to show. The proof of the other case, when L is less than 0 and k is some number between 0 and L, is exactly the same as the previous case and is left as an exercise for the viewer. Now let us see some interesting corollaries of the previous proposition. If xn and yn are two converging sequences such that xn is less than equal to yn for all n, or at least after some n naught, then limit xn as n tends to infinity is less than equal to limit yn as n tends to infinity. Let us see a proof of this. Let L be limit xn as n tends to infinity and let M be limit yn as n tends to infinity. We want to show that L is less than equal to M. We will prove this by contradiction. Suppose L is strictly bigger than M. So as shown in the figure, L is strictly bigger than M. Now let us take epsilon equal to L minus M by 2, which is half of the difference between L and M. Since xn converges to L and yn converges to M, by the definition of limits, it follows that xn belongs to n epsilon L for all n greater than equal to n naught, and yn belongs to n epsilon M for all n greater than equal to, say, n naught tilde, where n naught and n naught tilde are some natural numbers. This means that for all n greater than equal to n naught, xn lies in this interval, and for all n greater than equal to n naught tilde, yn lies in this interval. If we take the maximum of n naught and n naught tilde, then we can conclude that for all n greater than equal to this maximum, xn is greater than L plus M by 2, which is the midpoint of L and M, and yn is less than L plus M by 2, which means that xn is strictly bigger than yn for all n greater than equal to maximum of n naught and n naught tilde. But this is a contradiction, since xn is given to be less than or equal to yn for all natural numbers n. Hence, our assumption that L is strictly bigger than M is incorrect, and hence L must be less than or equal to M. Now it follows immediately that if xn is greater than equal to 0 and limit xn is equal to L, then L must be greater than equal to 0, and this can be proven easily by taking yn equal to the constant sequence 0 in the previous example. Similarly, if xn converges to L, which is not equal to 0, then there exists a natural number n naught such that mod xn is strictly bigger than mod L by 2 for all n greater than equal to n naught. I shall give a hint to prove this result. Since xn converges to L, this implies that mod xn converges to mod L by proposition 6, which we have already proven. Now it is enough to take k equal to mod L by 2. Remember, k is a number between 0 and mod L. So take k equal to mod L by 2 in proposition 7 and prove this result yourself. I shall stop at this point. In the next lecture, we shall define subsequences and I shall give a proposition which relates the convergence of a sequence to that of its subsequences. Further, we shall also look at what is called the algebra of limits. Thank you.